Our next speaker I've known for 51 years. Uh, and he swears to me that in his talk there will be no mention of duct tape or any such mechanisms. Thank you, Doctor.
Thank you, Greg. My name is Douglas Thane from the University of Notre Dame. And my talk here is Wrangling Complex Notebook Workflows with Floability. And I'm speaking on behalf of the entire Floability team, which includes folks from Notre Dame, University of Missouri, DePaul, and Illinois. Oh, am I speaking here? It's working. Yeah, okay, good. Okay, so then I can wander. I can wander. Okay, good. All right, so actually, I really enjoyed this talk just now, and I think this is actually a bit of a continuation on a theme here. I'm very comfortable in this high throughput world, and I'm a Unix propeller head. And so when people talk about computing, I think about VI, files, processes, Condor Q, kill, ls-lr, right? This is the world I live in. And those terms are very comfortable over here on the right when we're talking about HT Condor, because that's the world that HT Condor grew up in. And the whole manual, the whole concept is organized around processes and command lines and all that good stuff. And if you're here, you're in, right? That's not a surprise to you. I regret to inform you that you people are weird. And I'm with you too, but I say this from a place of love. You're weird, because this is not how people born in the 21st century do their computing. And when I talk to brand new graduate students in computer science even, and ask them how they do their work, the first thing they do is they open up a web browser, and they go to a notebook like Jupyter. They import some Python libraries. In the middle of their Python program, there'll be a shebang that says pip install some software. And, this is making me very nervous about what they're doing. But this is a really powerful, interesting environment, right? So if you're doing data analysis or biology or even high energy physics, right? It's interactive, it's fast, it's responsive, it's graphical, it's got all these wonderful Python libraries, it works with your GPU. This is where people start. And it's really difficult to jump from here to here, right? And actually, it's very much in the spirit of starting with snake-make, right? If you live in a Python world, that's where you begin. And how do we get people to go from here to there? And I think it begins with a recognition that nobody starts with the cluster, right? Nobody sits down to do their science and says, I want to use a cluster. That's not what they do. Right? They start with their data, they start with some algorithm that they want to write, and they start on their laptop. And you can get a long way on your laptop because your laptop's got a GPU on it, probably, and it's got a fair number of cores. And so you can write your algorithm, you get started, you've got some toy data, you can even parallelize on your laptop. So there are a lot of people writing code using Dast on their laptop, and you can get going on 16 or 32 cores. And you got to remember, there's a lot of people in this world who solve their problem by saying, if I spend $2,000, I can get a bigger laptop, right? And now my research goes twice as fast and I've really accomplished something. But sooner or later, you hit the limits. And when you hit the limits, you have to figure out how are we going to jump from the laptop environment of the notebook that already has this complicated parallel workflow kind of thing in it, and how are we going to get it on the cluster? Did I say nobody starts with high throughput? Yeah, the asterisk there says nobody born in the 21st century. Yeah, that's what they meant. Sorry. Okay, so that's the genesis of the Floability project. So we have an NSF-funded project here in which we aim to enable the rapid and portable deployment of notebooks expressing complex scientific workflows across a wide range of cyber infrastructure. And really, the notebook and workflow parts are both essential here, because notebooks are important. If you just have a notebook, I think that isn't parallel or distributed in behind it, then I think we know how to do that, right? We have facilities that let you deploy notebooks, and those are cool. But here, we're really focused on this connection of notebooks that want to do complex parallel workflows in their back end, and then how do we hook them up with cyber infrastructure. So this is our sort of overall project goal. And we usually start with this sort of observation. People can get this stuff working, right? I get it working on my laptop, and a notebook is like an iceberg, right? There's the thing you see at the top, which is the browser and the code and shift return on the cells and all that. But underneath the iceberg, there's an enormous quantity of stuff necessary to make your notebook go. So there is the workflow that is expressed in that notebook, right? Maybe that comes with via Dask or Ray or Parcel, or I bet you can even do snake-make in a notebook. That's probably a thing you can do. And of course, none of that works until you have the proper software installed. Of course, that doesn't work either unless you have the data present on your site. And then you've got the cluster underneath that has a certain amount of resources to make it work. And so you could probably get this going in one place, but it requires an expert, probably somebody, the sort of person sitting in this room in order to get that whole stack of stuff working. And we see this all the time, that somebody gets this complicated thing working, they write the paper, and they say, hey, I've got this great notebook, let me give it to you. And they give you the notebook, and nothing works, right? Because all you did was pass along the thing that's at the top of that iceberg. All right, so our starting point here that we're going to use to enable new ways of thinking about these notebook workflows is to say, first we have to encapsulate all the things that we are doing. And this encapsulation we call a backpack, right? Because you've got your notebook and all your stuff, and you can't just carry that around. You got to get your backpack, you got to put all your stuff in your backpack, and you carry that to a new site, and then you can use it. So what's in a backpack? Well, in principle, in the abstract here, you've got the notebook itself, which is the interactive thing with cells. You have the workflow expressed within that notebook. You have some specification of the software that you need to run the whole thing. You have a specification of the data, and you also have a specification of the resources that you need, right? How many CPUs, how many cores, how much disk space, how many GPUs. If you like, a backpack is sort of like a Condor submit file for the whole shebang of a workflow. So if we can get a workflow expressed in this way, then a backpack is the thing that we can deploy using Floability. So over on the left-hand side here, we have the backpack with its specification. And using some of the Floability tools, we can take that backpack and automatically deploy it into a facility. And that deployment is a bit complicated because it involves things that have to happen at the front end to deploy that notebook in its environment, and also things that have to happen in the cluster as well, and those two things have to be coordinated. So if we can have a backpack like this, we can have a tool to deploy it, and it will put the notebook and all the components that need to be there at the manager side of things. It will deploy jobs that then carry all the things that the workers need. And then those two things work together, they stand them up, and now the user comes in and interacts with that front-end notebook. And from the user's perspective, it's just a notebook. They see the tip of the iceberg, and deep down there in the cluster, we've got all the rest of the ice and the water and the penguins and the whales and all the things that need to be swimming around in order to make this nice interactive thing work, powered by high-throughput computing in the back end. All right, now, you always have to start with applications. And well, I have a tendency to start with high energy physics. That's kind of in my DNA. And so we've been working for a long time with the CMS group at Notre Dame to build novel data analysis applications. And in the old days, we started with kind of the old-fashioned Unix propeller head interface. But now all of these physics graduate students come in, and the first thing they do is they write Python. And so we have these very nice data analysis applications that are expressed in very high level Python. They make use of NumPy constructs. They make use of the Coffee data analysis framework. And so they can write things that are actually quite impressive in like a kilobyte of code, in which they express their high level data structures. And then they use things like Dask to parallelize processing on those data structures. And so we've written a bunch of papers and whatnot about how to take these analysis applications and scale them up. And these aren't as big as the production things that run all day long across the entire grid, but on one site, we're talking things on the order of 10,000 tasks on the order of terabytes of input data, terabytes of intermediate data, and then when you're all done, you get out a kilobyte of data, and that's pretty good because what that means is you can display it right in the notebook, and then you're all done. All right, so we have some of these notebook applications going that are running on our HT Condor pool at the University of Notre Dame. And actually, this is the thing we backpacked up the most well. Now, truth in advertising, I'm going to start to reveal here. We're in the early stages of the project. Things don't all work yet. They're not complete. That's okay. But here are some other applications that we're working on. So we've been working with our friend Harsha. Yeah, there he is. Hi. So Harsha gave a very nice talk yesterday about his applications, which are already notebooked up very nicely, and they're already using Dask. And so a nice application that we can run is based on the Common Earth Systems model, which the LENS data set, which reflects 250 years of Monte Carlo simulations about the Earth's climate. And this particular job is using Dask to pull these down and then in parallel compute things like, has the surface ocean heat content increased with time over January of every year, and produce these lovely visualizations in the notebook. So yeah, so this is all backpacked up, and we can run this at a couple of sites. I'll get that into a minute. Here's another application that we're working on. This is an aging dam simulation that comes from the iGuide facility at Illinois. And this is a really interesting GIS application in which we have geographic models of the Earth, the locations of dam infrastructure, and the waters that they're holding back. And the questions here are, as dams increase in age and risks increase, what happens when one of those dams fails, and where's the water going to go as it flows across the landscape? And so there are all sorts of different ways we can look at what are the risks to people living in mobile homes, what are the risks to people who are old and have difficulty moving out, what are risks to people who don't have vehicles, that sort of thing. And so in the spirit of a work in progress, this is something we have converted to a backpack, but not converted to distributed execution yet. All right, so these are the sort of applications that we're talking about. And I know you're all asking, but what's really in a backpack? And so I just want to describe to you backpack version 1, keeping in mind that there is an underlying concept here that we want to track the workflow, the software, the data, and the compute. There are a variety of ways to capture that. This is our first, most straightforward way of capturing what some of those things mean. All right, so what's in the workflow part of a backpack? Well, a Jupyter notebook with code that you've seen before. It's the end of that. Same thing you would normally write. What's in that software component? Well, here what we do is we capture a whole bunch of Conda dependencies. And we have to be quite specific here that you can't just put in random names here. You need version numbers because this thing has to resolve quickly, and it has to resolve the same way every time. And we capture a software environment for the manager, but we also capture a software environment for the worker. And for most applications, the worker environment is smaller than the manager environment. And this is good because if you're going to scale out to 1,000 nodes, it'd be nice if we had a smaller Docker container. For this particular application, the worker turned out to have more dependencies than the manager. But that was a little unexpected. Now, if you've ever worked with software dependencies in this way, sometimes you don't actually know what's happening in that application. Or maybe you know what's happening in the application, but you don't know what the manager needs versus what the worker needs because it's decomposed at runtime. And so we have this neat SciUnit technology that comes from the team at DePaul. And what SciUnit does is it takes your Python application and it traces it to figure out what are the libraries that you're actually using. Not just what did you put in import at the top, what are the libraries that you're actually using. So if you're elevating a notebook into a backpack, you do some tracing here. We can then infer from that tracing what are the Conda and pip software dependencies, as well as maybe what are some of the data dependencies that you didn't mention. And this turns out to be important for packaging for reproducibility. Where we're going with this is eventually we want to get down to the point of saying what are the dependencies used by each cell in the notebook so we can break it down a little farther. All right, so coming back to the backpack here, there's a data section. Now, the data section is a listing of all the data that this workflow expects to use. Now, in the simple case, you can just put some data in the backpack. If you've got, a couple megabytes of files, we can just put them right there in the data section, and this here will say, okay, here's the data source. Let me tell you where to put it in the workflows sandbox. But really, in high energy physics is a great example here. What if you have a workflow that's going to consume 10 terabytes worth of data? It doesn't really make sense to pack that up into a backpack and put it in a Git repo. That's crazy. So what we really want to do here is connect to Pelican and the OSDF so that we can mention the data needed through a global namespace and have the system either pull it down into a sandbox or stream it to the execution nodes as it goes. And then finally, we need to describe what are the compute resources. And in here, we're using the Vine factory to get a certain number of workers with a certain number of cores, memory, disk, and so forth. Okay, so what are the mechanics of this? Well, Backpack is pretty straightforward to explain. There's a fair amount of steps for this thing to actually work. So if we think about what this Floability tool is going to do, it's going to read in this backpack up at the top that describes all the pieces of the entire workflow, and is going to create an executing instance. And now Greg is going to pick on me about instance versus image versus backpack. Okay, we'll talk to him to get all that sorted out. Sometimes the mix of metaphors are hard, right? Do backpacks have instances? There's a lunchbox in here somewhere that okay. All right, so the user's going to say, hey, please deploy this backpack. And so we begin by taking all of these things out of the backpack. The backpack's immutable. So we pull out the workflow and we pull out the data specification. There's a little cache there to indicate that this is a thing we may already have. So if you run similar workflows, you don't keep downloading the same stuff over and over again. And then we go and build tarballs based on the software environments that you specified. Then we can deploy the software environment for the manager side of things. We have to link the data into the namespace, and then we can run the actual notebook. We can run the actual notebook from the workflow, and we call this the manager side of things. Once that's in place, we take the worker's environment, we give it to the factory talks to HT Condor or whatever your batch system is, and dynamically submits workers. I couldn't squeeze in multiple workers here because I wanted to point out, sort of goes back to that nesting of containers things, right? You've got the batch system, then you've got a job. In that job, you're going to create a software environment. In that software environment, you're going to create a worker, and then the worker is going to come back to the manager, and then the manager is going to send it tasks to run. So there's a lot of things to stack up. Okay, but that's the flow, and if we do all those things, now we have an interactive access point that the user can pop in here. They can run their normal work. They can run their normal workflow, and whenever they define a task or some parallel action, then those tasks will run out here at the workers they have deployed in the cluster. So that's the mechanism of how it works. Now, by the way, let me preface this by saying this is my latest complaint in PhD defenses. Whenever somebody puts up a table, they fill it with checkboxes, and their stuff has all the checkboxes, all the things checked, and nobody else is checked. So I insisted we added some columns here to show not just the things we've done, but also the things that we haven't done. So we have a nice examples repository collecting various applications here. And the good news is this has been reasonably portable so far, and we've been able to make it work at Notre Dame, at Purdue, at Texas, at AWS. Some applications a little harder to pull together. So Montage is this classic workflow benchmark. And being from a little older age, it doesn't have all the software dependencies nicely referenced in a repository. A little tricky to make it work. And so we haven't figured out how to make that portable yet. And we would love to run this stuff at the OS pool. Really, the only barrier to that right now is we need to be able to get our worker to connect back to the manager. And so I've had some discussions with Brian and Brian and some other people, and I'm hoping that's something we can work on so we can fill out those checkboxes and get these applications running on the OS pool. I think I'll skip through this. This is just some figures demonstrating that things do work, and when you come back to them later, they run faster because you've already built some of the things that you need. All right, so big picture. Floability is a 4-year project. We're in year 1 of a translational research project. And I like to think we've sort of reached our MVP. We have a thing we can share now. We can try it out. We haven't reached all our goals yet. It's available via Conda and on the web. And we're looking for applications and some brave initial users. And so if either you have an application or you think of a user for which this might be useful, we'd like to talk to you. And I'm not saying we've got something we can throw at you and it's going to work right away, but we'd like to talk to you, and I think there's an opportunity there. Now, really, the backpack is just the first step to sort of thinking about this more deeply. As I said, a backpack is sort of like a Condor submit file for a whole complicated workflow. So I would love to be able to use that to do some resource management. And I like to say no. So I want to find more ways that we can say no before we run this. You've told me what data you need. Maybe I should check to see if we have 10 terabytes here before we do that. Greg is giving me the no finger, yes. You've asked for 100 workers of a certain GPU type. But maybe before we start standing all this stuff up, we should see if that pool actually has that resource. And actually, I love saying no, because the sooner we say no, the easier it is to give the user some actionable information, some explanation. And it's much better to say no up front than it is to have a problem at runtime. I think we have some interesting problems to work on in reconciling interactive and batch allocation. Right? So I think these big systems do a great job of managing the resources of the cluster. But this whole idea of having a front end where you stand things up that are related to the things that run in the cluster is less developed. Right? And it doesn't make sense to do one of those things without the other. Another thing I've come to learn, I no longer say our software works on HD Condor everywhere, or our software works on Slurm everywhere, because there's so many ways all the sites are different, and it's really more truthful to say, well, we ran it at Notre Dame, we ran it at Wisconsin, we ran it at Purdue. Those are the places we know that it works. And I think there's some work to be done to sort of capture some of these site specializations, right? Where's the shared file system? Where's the temporary? What are the size of things? And it might be worthwhile to figure out, how do we capture and describe sites as distinctive entities, as opposed to just saying, well, it runs a certain batch system. And finally, this is a little more forward-leaning. I think it would be really interesting if we can take notebooks, and instead of asking the user to write parallel code, we could say, well, maybe the notebook already expresses some parallelism. Maybe these two cells are independent. Maybe we already ran a cell like that. Maybe a notebook is actually kind of like a makefile if we just go ahead and write the code in the normal way. So I think there's some interesting opportunities there. All right, so I want to thank all of the members of the team who've been working on this. And you can check out some information about Floability there, and I'd be happy to take questions. Thank you.
Thank you, Doug. As always, thought-provoking or challenging. So, on one hand, this is something we have been struggling with from the outset, is how do we determine the dependencies of an application, what do you call them, the DLLs of and all your arrows are sort of going in one direction, and we always struggled with what happens if we get something wrong. And suddenly your notebook in step God knows what is trying to invoke something. That's the reason why I hate CVMFS, because and you also stress, okay, can I tell you in advance that it will not work? But again, it's the easy part that you detected. So any thoughts? And I know you have a 2004 paper on error propagation. And what happened if, you know, you spill your water in your backpack and and suddenly all your food is I don't know, whatever it is. Any thoughts about how stuff goes back to the researcher that is used to the laptop? You know, if the laptop it doesn't work, you close the lid and open it again, and suddenly it works, right?
So maybe this is a little countercultural. You know, one of the speeches I give to students in my compilers class is to say, you should be thankful that the compiler finds so many errors from your code and refuses to run it, right? There's a dialogue between the person creating the thing and the machine checking it. And I think that
and then I have to add that then you get the warning and you turn them off.
But I think there's an opportunity for us to think about more of a dialogue between specification and tracing and execution, right? So, you know, for example, there are Python tools that tell you, hey, you imported something, but you didn't use it. It actually turns out that's really important for resource management, for tracing and so forth. I would love to have a tool that says, hey, you ran this workflow and it worked here, but you know what? You opened that file and you didn't say anything about that. Maybe that's something you should check into, right? Or, you know, I took this Python program and I threw it over there and I ran it, and you did an import that wasn't there. And you know what I did? I went and installed for you anyway. You're welcome. But I'm telling you now that this is slowing you down. And so, right, there's, I think, an opportunity for dialogue between specification, attempt, repair that doesn't have to be so brittle, but there's an opportunity to give feedback to the end user to make it better.
Yeah, did you think about how would you communicate? Let's say in a postmortem. So one of the things that we are struggling with is, okay, you found all these things, how much memory you used and how much this and da. How do you report it back after you are done running the backpack? How do you present it in a way that is meaningful, is searchable, is accessible after running all these things, and say what happened? Because, okay, you didn't use this Python here because of the data, and in this data set you did use it. So it's data dependent. It's not. Before your brother starts throwing a sharp object at me, I will shut up.
It's a very challenging problem. I don't have a simple answer to it, but I think it's a good problem.
And maybe it's an easier to start it not real time and post-mortem. That would be a step to the harder part.
Yeah.
One quick thing, I'm a little disappointed, Doug, for someone who wrote a compiler book, that you didn't refer to this as transferring backpacks by value and not by reference. Yeah. So thank you, Doug. A round of applause for